There we go. Thank you. I hit recording. Okay, so now we're recording. Let me reintroduce everyone again. This is it's December 5th, 2020, and I'm Stokes McMillan, and welcome to the NASA Alumni League virtual program, our first Thursday program for December. And today we have Dr. Kirsten Siebach, who's going to talk to us about Mars. So Dr. Siebach is an assistant professor at Rice University's Department of Earth, Environmental, and Planetary Sciences, and she calls herself a Martian geologist. She researches sedimentary processes on Mars and early Earth to interpret the history of water and surface environments early in our solar system. Kirsten earned her PhD in geology at Caltech, working on the data returned from Mars rovers. She worked on the science and engineering teams for the Phoenix lander and the two Martian exploration rovers, Spirit and Opportunity. She's currently a member of the science and operations team for the Mars Science Laboratory, more commonly known as the Curiosity rover. And recently, she was honored to be selected as a participating scientist for the Perseverance rover that will land on Mars in February of 2021. And now let me hand it over to Dr. Kirsten Siebach. Kirsten, you might want to share your screen.
Thank you. Yes, let me get my screen sharing up. And make sure it's still got you guys. And my slides. All right. Wonderful. Well, thank you so much for the invitation. It's fun to get to speak to people, even if we're kind of confined to our own homes, and get to see you guys. And I'm excited to tell you about what we've been learning about Mars and kind of reading the rock record of Mars and what that process is like. I'll be focusing mostly today on Curiosity rover observations, because that's the big mission we've been working on for about the last 8.5 years. But introducing the Perseverance rover just at the end. And I just wanted to start by thanking, as you guys know, nothing at NASA happens without a huge team of people behind it. So everything that I'm going to share today about the rover traverse and about the science that we've been doing is really thanks to a huge team, the science and engineering team for the Mars Science Laboratory, as well as some of the folks in my group who have been doing research that I'll mention here. All right, but stepping back, you know, when we think about Mars, humans have been thinking about Mars for thousands of years, and the Egyptians traced it as a planet in the sky. They noticed it. As soon as we could develop telescopes, we looked at it more closely, right? And this was the first published map of the surface of Mars back in 1877 by an Italian astronomer, Schiaparelli. And he looked through his telescope and mapped out the features he could see on the surface. And you'll note he actually has all of these straight lines crossing significant portions of the center part of the planet between the dark northern hemisphere and the lighter southern hemisphere. We still don't know exactly what those straight lines were that he was mapping out, but he called them canali, or some kind of channels. The English heard that, thought that there were canals, which they were in the process of building in the 1870s in order to transport goods. And so they immediately interpreted that Mars must hold some kind of really advanced civilization because they've already figured out how to transport goods across the whole planet. And that set off, you know, several decades of watching Mars, thinking of it as this planet with advanced civilizations, with life, with some kind of beings that we could potentially interact with. And so when we did get to the space era and actually send spacecraft, we were actually relatively disappointed to find that instead we had mostly a dry, barren surface that was covered in craters. Several of the surfaces were more ancient than any surfaces we see on Earth, closer to the surface of the moon, more than 4 billion years old. And so it was actually a little bit disappointing, but we did notice even early on that that wasn't the whole story, that parts of the surface had been crisscrossed by water, and it had left large channels and canyons, sometimes as large as the United States itself. Valles Marineris would cross from California to New York as a huge canyon. You can also see from that Viking image in the background here that there is actually water ice at the North Pole and the South Pole. And so there is water there today, and there was clearly flowing water there in the ancient past. And so the question became, you know, what was it like then, and could we possibly figure it out? And that latter part is kind of critical to how we had to approach this problem. So on Earth, we have plate tectonics, and plate tectonics is constantly recycling the surface of the Earth, recycling the Earth's crust. It's pushing oceanic crust under continental crust, pushing mountains up, changing everything. And it means that really old crust is very hard to find on Earth. Less than 1% of the crust that's older than 3.5 billion years still remains. And we haven't found any older than 4 billion years old. But the advantage of plate tectonics is that by recycling the crust and by pushing up these different rocks, you actually expose ancient sedimentary rocks that were once buried. And those ancient sedimentary rocks are the key to understanding the history of the Earth and actually mapping out the history of fossils, the history of life, the history of climates across our planet, the history of surface environments. So with Mars, at this phase in the 1970s, we realized that indeed there was significant evacuation of the surface by water, and there is still water on Mars in the form of ice. But we weren't sure if any of the story of that time when there was water would actually be preserved or accessible, whether there were any sedimentary rocks or whether we'd be able to find them. And that actually took another just over 20 years. There was a seminal paper in the year 2000, and I'll walk through one of the sites that they pointed out as they looked across the surface of Mars. It was this area. This larger crater is called the Holden crater, and the smaller crater is called Eberswalde. And so let me grab the chat just so that, okay. The smaller crater right here, it's more ancient, it's much smaller. I've got a gray circle so I can outline it so you can actually see, but this is a small, older crater. It's actually been partially infilled by the ejecta of this Holden crater. These two craters are part of one of these channel systems. And so those channels that cross-cut big swaths of Mars and show that water must have kind of flooded across the surface and really carved out these big canyons. Well, one of those canyons goes into Holden crater, and it actually cut right out of Holden crater, which means the whole crater was full of water. And it loops around over the top of this image, and you can actually see part of the channel right here leading down to this white box. And this white box is where that ancient channel enters into the depression created by this ancient crater. And if we zoom in on the white box, you can see this deposit. This is an inverted delta deposit. So that river that was coming around after having evacuated, actually flooded right out of Holden crater, came around, entered into this depression. The depression, the Eberswalde crater, contained a lake at that time. And that river, carrying whatever sediment it was carrying, flushing down, hits that lake and immediately starts to drop its sediment, right? So the water, as it's moving fast, can carry large particles. As soon as it hits the lake, that water slows down and the particles fall down. And so what you're seeing here is actually, basically, these are the traces of the river entering into that lake, and it wiggles around through time. Now, of course, when you're actually depositing sediment, when you're looking at a river, the river is a depression. And so originally these were depressions surrounded by mud, surrounded by kind of sediment that would have been falling down in the lake. But today they're cliffs, right? Today, these river traces are elevated above the surrounding topography and preserved. And so what we realized here, what we realized with this seminal paper in the year 2000, just 20 years ago, was that in fact, sedimentary rocks were formed on Mars and they have been exposed. Now in this case, they're probably just exposed by wind. You've had really powerful wind action on Mars for about the last 3 billion years. Now it's not powerful enough to knock Matt Damon over, right? But it is powerful enough that over time, it has actually exposed some of these ancient rocks, and it's moved all of the muds out of the way for this case, and left those sedimentary rocks, which then, if we went and visited this area with a rover, we could see, what was upstream, what's in the particles being carried, and what the environments were like based on how those particles were weathered, how they're distributed in this delta, what the chemistry is. So we could start to interpret ancient environments on Mars by going to this site. Okay, so now from 20 years ago, we know, okay, there are sedimentary rocks and there are places where they're exposed. So that set us up for thinking about, what's the history of Mars and how could we investigate it? To step back and put that history in a timeline here, I'm comparing Earth and Mars here, and on the left is 4.5 billion years ago when both planets formed. And you go over to the right, you get to today. Now, if we look at Earth, most of Earth's surface is going to reflect about the last billion years. And that's because plate tectonics is constantly recycling everything. And really, a lot of Earth's surface is going to reflect the last 200,000 years or so because of ocean floor deposits. But we know that there were really critical events that we find in the rock record that's older, like the rise of atmospheric oxygen, and especially evidence for the beginning of life. We think the origin of life on Earth happened sometime around 3.5 to 4 billion years ago. But like I said, less than 1% of the crust from that time is preserved, and most of it has been dramatically altered by metamorphism and repeated plate tectonics. So it's hard to find really good evidence for what the surface was like at that time, and to even find fossils that many groups agree on. Now, Mars provides us this really interesting case study where actually most of Mars's surface is from this time between about 3 and 4 billion years ago, including rocks that are more ancient than any that we find on Earth. And when we've traced out the mineralogy of different parts of the surface, and this is based on the mineralogy is from spectroscopic work from orbiters, and the ages are based on approximations based on the number of craters that have hit the surface. So if you have a surface completely saturated in craters, it's older than one with just a handful. And we realized that, in fact, on Mars, before about 3.5 billion years ago, there were a lot of clay deposits. We see a lot of phyllosilic mineral clays. And so at that time, Mars had significant water interacting with the rock and altering the rock to form mineralogical evidence of that water interaction. Over the next 500 million years, we'll see kind of an influx of salts. We'll see these thick deposits of sulfates. Usually on Earth, we would think of carbonate deposits because our carbon dioxide atmosphere gets integrated with the ocean and left in carbonates or limestones. But on Mars, we actually mostly see sulfates. And then from about 3 billion years on, Mars is pretty dry. We do see canyons carved after that time, but they appear to be kind of large flood deposits where some water evacuated part of the surface briefly, but it didn't leave as much of a mineralogical trace. And really the wind has dominated for those last 3 billion years as an erosive actor on the surface of Mars. So Mars ends up having this great record of a time that we can barely visit on Earth, that we struggle to find good records of on Earth. And in fact, it's the time when we think life evolved. So I go back and forth. I get really excited by Mars today, but it's pretty dry. It's just kind of windy. We get to observe the wind action. But when we think of Mars in the past, when we get to visualize what it's like 4 billion years ago, it really provides a window into what Earth might have been like, what the origin of life might have been like, what geological processes, what we can't see because we're on Earth at a time when it's covered in life and covered in water and in a specific climate state. Mars gives us this example of a foreign planet, but something that might have been similar to early Earth, which actually turns out to be kind of a foreign planet as well. And when we can actually look at Mars, we can trace out, how did the geology work in this time when life hadn't started? And some of that would probably be very similar between the two planets because as far as we know, they looked pretty similar about 4 billion years ago. Okay, so that's part of my excitement with the geology of Mars and these ancient rocks. And so as we got up to around 2012, we were looking at different landing sites where we would land Curiosity. It's actually in 2011. And based on the story I've just told, it becomes pretty clear why we picked Gale Crater. You know, you need a site that balances between geology and engineering. Geologists always want to go to the Grand Canyon, and it turns out if you're an engineer and you're trying to land a rover on Mars, you probably want to land in Kansas. So it's very flat and safe, right? And this one provides a great balance. Gale Crater is an impact crater from about 3.7 billion years ago. It's 110 miles across. So maybe that's similar to Houston. It's pretty big. It's got a central peak right in the middle of it. You can see this rocky peak is actually about as tall as the crater itself. It reaches the same height as the rim of the crater, which is about 5 kilometers above the base of the crater. So what happened there is that the impactor came in and hit Mars so hard that it not only evacuated this hole in the ground, actually part of the hole rebounded and created a central peak right in the middle, just like a drop of water in slow motion kind of thing. You know, since then, this crater filled up with sediment. And interestingly, it probably filled up a lot more than it's filled today and could have filled more than once. But then that wind came back, and there are different reasons why the wind might have changed so dramatically. But today we're in a phase where that wind is really active. And the wind is actually currently blowing into the crater from this side and blowing what appears this dark sand. It looks really dark because it's active and it's not covered in dust. Most things on Mars are covered in red dust. So this dark sand is actually currently being blown around the edges of the crater, around that central peak, and whatever sediment has still been stuck to it. It's actually eroding out parts of the floor of the crater and the sides, and then it actually blows right out the back of the crater. So that's happening today, and that probably happened for a very long time, because we can actually see layers and layers, kilometers of exposed sedimentary layers in the crater right here. And if we look at these with a spectrometer, it's one of the only places on Mars where we have exposed layers that show us the time, if you look at this column on the left, just generally from older to younger, it's got the time when there were clays deposited, and then it's got thick layers of sulfate salts, the yellow, and then it's got dry Mars on top. And if you look over here, they're kind of lined up in these layers right here, and this is all dry Mars, the top 70 or 80% of this mountain. So the floor of the crater provided a safe place to land. It's kind of the moat around this central peak, provided this nice flat place to land. And then we drive over, and actually we have to skirt around these dark sand dunes that are still blowing to get to those layers of sediment. And for that adventure, we got to use the Curiosity rover, Mars Science Laboratory. This is about the size of a small SUV. It's quite a large robot. It contains 11 different science instruments, something like 17 cameras. It's built to be a laboratory. So it's built to kind of be a self-encompassed way to search across Mars, take samples. It has a 2.4 meter long arm that reaches out, and it's got a drill and a scoop at the end of it. It's also got a camera and a way to measure chemistry, XRF. So it can drill into the rock, take a sample, and then it has a mass spec and an XRD on board. So we can actually do kind of a number of laboratory analyses with this one robot driving around as kind of a self-encompassed mobile laboratory and geologist. The fun instrument in this, artist rendition here is the ChemCam, which is the laser, which can do laser-induced breakdown spectroscopy, which means it zaps a rock between 7 and 20 feet away and zaps a tiny spot into a plasma, looks at the plasma to determine the chemical constituents of the rock. So it gives us kind of elemental chemistry from a distance, and we get to choose what we want to zap with the laser that day. So it is a kind of a fun instrument. So Curiosity landed on August 5th, 2012, actually almost exactly where we'd hoped, right in the middle of that ellipse in Gale Crater, just a little downstream of the center. It had a parachute landing, which actually was captured in a real image by the Mars Reconnaissance Orbiter, which was orbiting Mars at the time and took this picture. still orbiting, still working, helps communicate. And then it was lowered slowly from something called a sky crane down to the surface of Mars. During that process, I love these pictures. So the sky crane is actually dropping the rover, and it's got the jets so that the rover doesn't actually have to have this fuel for the landing system. These jets are blasting out propellant. You can actually see this picture was taken from the bottom of the rover while it was landing. And so what you're seeing here are the dust clouds being blown away by these jets of propellant as it's landing. And you see that it's stronger on one side than the other side. And that's because there was a little bit of wind, and we were trying to cut the horizontal velocity created by the wind to make sure this rover went down safely. I always think the engineering involved here is just truly amazing. And it's so cool to have this chance to work on this rover that's been so beautifully delivered to the surface. And so it landed totally safely, beautifully, and they kind of hand the keys over to the science team. From our landing site, this is one of the first pictures of actually looking over towards that main mountain where we've preserved all those layers of Mars history. And so we call the mountain Mount Sharp. You can actually see in this image the dark sand that's blowing around the mountain. Some of these darker recessive layers contain the brightest signature of phyllosilicate clays, mineral clays observed from orbit. The really nice layers above that with kind of clearly defined horizontal lines here are the sulfate salts. And then above the dotted line, you see the angle changes. And above that line, we don't see as many indicators of water, and instead it looks like dry dust, iron oxide material. So we were pretty excited. This is an overhead. This is the dust blast out at our landing site. So this is a false color image, so it shows up kind of blue. And this is the way to Mount Sharp. And we've taken that picture. We're all really excited. We've selected this landing site. And this always makes me laugh that we have about 500 people on the science team, and you've got one car. You got to decide which way to drive. In this case, I think it was the most obvious time in the entire mission, and yet we actually almost unanimously, also the only time that happened, chose to drive over this way. The reason for that was because this light tone layer that you can see in the upper right-hand corner is the lowest unit in Gale. And so it's the lowest exposed unit on the floor of the crater on this side. And we know water runs downhill, right? So we just wanted to start there. It was about 500 meters away. We're about 8 kilometers from the mountain. So we drove over, and this is actually one of the images taken by the Mars Reconnaissance Orbiter, the same one that captured Curiosity dangling from the parachute. And you can see the rover tracks and the rover right here. So that's Curiosity during that first jaunt. Some of the first rocks we found, I'll just recap part of the initial story because that light tone deposit turned out to be really important. These rocks were blasted off by the jets as it was landing. They're conglomerates. So you can actually see in these rocks, there are rounded pebbles, and those rounded pebbles were rounded by water, and they're too big to be blown by the wind. So they must have been carried by water. And based on the size of the pebbles, we can back out the depth and kind of speed of the water that was carrying them and say that this is probably a river that's something around knee to waist deep. So we landed immediately on top of an ancient river that was knee to waist deep, which was pretty exciting. We started driving. We found a lot of indications that there was a lot of sand and kind of pebbly sands that were deposited in rivers where we could actually see stratification or the layers formed as ripples on the bottom of the river migrate. And we stepped down into that light tone deposit that we'd identified from orbit as the lowest unit. This gives it away a little bit. It's called the sheepbed mudstone. This was the point where we really got to test all of our analytical instruments on board the rover. And so just to give you a sense of some of the key instruments on the rover, we have that laser that I mentioned before. That gives us these little 300 micron, spots zapping different little tiny freckles on the rocks. We can also drive up to the rock, and with the arm, on the arm, we have this XRF-based instrument that's called an APXS, and we can hold that up to the rock and get the bulk surface chemistry of a spot around the size of a penny. This is an example on a sandstone of what that would look like. Then on the same arm, we have a drill, and the drill will actually drill about 5 centimeters deep, again, about the size of a penny across, and about 5 centimeters deep, and actually sample the rock itself. And this was one of the first rocks we sampled in that mudstone. And one of the exciting things to first order was just that when we drilled, the rock was gray instead of red. Now, all of Mars is red all the time because it's covered in this iron oxide dust. Gray rock contains reduced iron. And so this already told us that there were kind of differences in the redox states of iron that could provide fuel for life. We took that drilled sample and delivered it to our XRD, which works in kind of an interesting way where the X-rays are reflected off the sample, which bounces instead of a giant X-ray arm that rotates, if you're familiar with XRD instruments. The idea of this is that the reflection of the X-rays across the minerals tells you about what minerals are contained in the sample. So we get the chemistry or which elements are in the rock, and then we get how they're bound together in the minerals. And what we noticed from this sample was a very high reflection at low 2 theta, which is from phyllosilicate clays, so those clay minerals, which turn out to make out about 25% of this sample. We could also heat it up in our mass spec oven, which goes up to something like 1500 degrees Fahrenheit. And from that, we could see a significant volume of water released, as well as some carbon dioxide and multiple redox states of sulfur. Now, putting that together, we're able to say this mudstone formed in a lake that would have been habitable for Earth-like life. And we define that as a place where there was water. The water wasn't super salty. There were clement conditions. That one's a little more fuzzy, but we can tell when we heat it up, when the water gets released, if there are a lot of salt compounds or kind of anything that would relate to a really high or low pH. This is a freshwater lake, basically. So there's water, clement conditions, all of the elements required for life, CHNOPS, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, all of those are present. There's energy that would be required for life. This comes not only in the form of sunlight, but also in those redox differences between different states of iron and sulfur. So there's chemical energy available for life. And all of those conditions lasted for some extended period of time. So in this case, these lake deposits, we could see that they covered at least 1.5 meters, or we could see about 1.5 meters of thickness of these lake deposits. And it takes on the order of 10,000 years or so to deposit that much mud. It's moving really slowly. It's just kind of sinking to the bottom of the lake. So we had a good little period of time with all the right conditions for life. So this spot, we've gone a lot further in the mission, but I always come back to this story because this really revolutionizes the way we think about Mars. We had said before that, you know, early Mars looked like early Earth, but this says early Mars really did have the environments where if life had existed 3.5 billion years ago, and if it had been like Earth life, it would have thrived in these environments. With that, we immediately turned to head back to the mountain and go investigate what happened next, right? The sedimentary layers, you get older and older layers on top, so you get to read the story if you go from the bottom up. So we headed towards Mount Sharp. We were actually pretty excited, and we had that 8-kilometer drive, so we started driving really quickly on the order of up to 150, 100 so meters a day. When we looked down at our wheels, we saw this image and we're pretty shocked. So the rover wheels were made of aluminum, and it was relatively thin. And unfortunately, it had been quite abused by the rocks that we were driving over. So the wheels we kind of tested, they were great for landing, even though it landed kind of hard on the ground after being lowered by that sky crane. And then they were set up to have as much surface area as possible so we wouldn't get stuck in a dune. Every other mission had gotten stuck in a sand deposit at some point. And so we set them up to be as wide and thin as possible. And it turns out the challenge here is that the wind has been blowing for the last 3 billion years, and it's actually kind of sharpened the rocks that the rover is driving over. So even though these are sedimentary rocks and may not be quite as hard otherwise, they're kind of shaped into points, and those points do not interact well with the rover wheels. You may have seen these other holes. These are intentional. These are meant to be a driving marker for how far if you look back at your tracks, you can see, you know, how many circumferences of the wheel we've passed. And the funny story about those is that they originally said JPL. NASA said you can't brand Mars, JPL. And so JPL put in these holes, and when it was launched and on its way to Mars, JPL released a press release saying it's JPL in Morse code. So these holes were intentional, say JPL in Morse code, so we leave that all over the surface. And then these holes came up, and those were slightly less flattering there. Now we immediately kind of convene a Tiger team. Obviously you can't do anything to fix the wheels, so the question is how to drive so that you minimize wheel damage, so that these aren't the thing that dies first. And of course, when you get a whole bunch of different experts on these questions in a room and say, you know, what's the safest way to go from A to B? We asked 5 people on this particular slide, and there are about 8 different paths here. It's just a challenge, right? It's a lot of communication, a lot of working with a big team to figure out which path will be the safest and how we can go through the terrain. And we ended up taking a path that at least initially followed this pink path and goes through some of these canyons, which gave us these beautiful views of the rocks. These two are these are right by point B. I'm gonna go back a slide. Right by point B, you can see some kind of stripy rocks or stripy looking deposits from the satellite image. When we got there, this is what they look like. And this is 2 different angles of the same little deposit of stripy rocks. And in the top image, the mountain is to the left, and the wall of the crater, the outside of the crater, is to the right. So the outside of the crater is over here. Here are those rocks. You can see the kind of stripes across here and some slopes inside of them. The image on the bottom, we're looking from the wall of the crater towards the central peak. And so head on, you can see these layers of rocks, and you can see that they're stacked up, kind of moving away from you like a bunch of pieces of paper slid over each other. And these are pebbly sandstones. And it turns out they're from a delta. So just like that Eberswalde delta I showed earlier, the rivers, they're coming in from the wall of the crater, coming across the crater, and right in this zone, they're being dropped, all the pebbles that they're carrying are being dropped because those rivers are entering into a lake and slowing down. And so this kind of shape, a little bit of a curvature that you'll see in this bottom schematic, and then you can sort of see it in the image above, tells us that we're in that same type of system. We're looking at where a river was entering into the lake. And indeed, soon after this, we got to reach the lake deposits. We head right over here, right? But we've been driving through river deposits across the floor of the crater, and this was what gave away that indeed the middle of the crater had held a much more extensive lake than the one we'd seen early on. And here are some of those lake deposits. They were kind of laminated, and so laminated deposits are just from either maybe freezing or seasonal changes, or it can be from storm events. So every time there's a storm, it washes in a bunch of water, carrying some sediment, lays it down, and then in between storms, there's a little bit of time with a different kind of deposit, and then you go back to another storm, flows in. So you get these alternating layers. Much of the rock has these millimeter scale alternating layers like you see on the right. Some of the rock, those layers get up to centimeter thickness like you see on the left. It could be that those are just different parts of the lake, or it could be that they're different time periods. And we don't know exactly the time captured in each layer, but we saw this initially. We saw a few meters of it. We are now, like I said, close to 8.5 years into the mission, and we have been driving through these types of laminated mudstones or similar styles of laminated mudstones for the past 6 years. We've actually driven up about 380 meters at this point worth of laminated mudstones. So the story I told where we had that 1.5 meters and we said, okay, we had a habitable environment and we had water and it was great for what it would have been life, lasted way longer than that. If we switch back to overhead images, I included the little picture of the crater over here for scale. We're looking at kind of driving or going this way. North is up, which is, well, I'm not sure. Maybe this little crater is more confusing. This gray at the upper left is the floor of the crater. The yellow is our traverse. The very dark are the sands that are blowing today. And we crossed over into the mudstones right about where you see a little lip here from darker gray to lighter gray. And then this is all climbing up the crater. There's a nice ridge line here that we investigated for a while. It's got some extra iron oxide. And then we cross this little trough, and that's where we are now. And let's see, I think I have, yeah. So the gray here is the river rocks coming into the little deltas. Then you kind of crawl across here. The light blue is all laminated mudstone. Every now and then we see some indicators of flow. So maybe some of the mud was exposed and there was some wind and there were dunes, or there was a river plume that kind of came in. So every now and then we'll see something like that. But mostly it's laminated mudstone. When we get up here, it's still laminated mudstone. We thought this was going to be different because it looked different from satellite imagery. The orange looked very iron oxide rich, and the purple was where we identified the strongest signature of clays. Turns out there's iron oxides through this whole blue layer. There's clays everywhere. The orange has kind of a little bit of extra hematite, and the purple has a little bit of extra clay. But for the most part, this maybe the most impressive thing is the amount of time that we had a habitable environment on Mars. If we put that in this image, always we've got to be careful with it because it's got a vertical exaggeration of 14. So to be clear, the rover does not drive up slopes this steep. It doesn't look quite like this while it's driving. But the point was just to say we've driven through so much of this material. And all the way along, we've been drilling into it and trying to understand, what it's made of and what it tells us. This is one of the times we've drilled recently. Each time this was during a global dust storm in 2018. So you can see it's actually really hard to see past these nearby rocks to the center of the crater, which usually it's much clearer. So the rover's pretty dusty at this point. I always want to include at least a couple of these little selfies. It actually takes us a full day on Mars to take a selfie. So, everybody snaps them with their phone all the time, but these actually require over 80 images, and the arm has to move in so many different contorted ways to get all of those images and actually cover the entire body of the rover, that it's quite an endeavor each time. And so we usually only take a selfie when we've stopped for a while to actually drill into the rock, which you can see in this image in 2018, the drill hole is still gray. So we're still looking at kind of an environment that had some reduced iron, had a lake. It's still pretty much habitable by our definition. Okay, to sum up, I'm going to sum up this story, tell you a little bit about what my group is working on, and then tell you where we're going. I'll sum it up with this little movie. Here's the rock 4 billion years ago. 3.7 billion years ago, you have your major impactor that produces a deep crater with a central peak. Sometime after that, there's water. There can be water coming in from groundwater, but importantly, what fills the crater is water coming in from the edge. That water is carrying particles. So first you drop your sand, your pebbles, your sand, and then you just drop mud in what was probably a shallow lake, but one that lasted for a particularly long time. Order hundreds of thousands, millions of years as this shallow lake. Could have dried up, we're not sure, but we don't see strong evidence for it. Above those layers, we have those slanted layers. These are probably windblown. So there's probably just wind that fills up the rest of the crater with dust and sand. Then the wind changes, right? And the wind starts to actually pull that out of the crater instead of putting it in. So it actually evacuates not only that dust and sand, but it evacuates the pebbles and the sand and the mud and leaves this major moat around the central peak. We know there are multiple episodes of groundwater. We know there are fractures that are filled and the rocks are changed, but eventually those dry up And then you get to 2012 and there's our little rover ready to explore, right? And so we saw it landed over here somewhere. We did see that one little bit of a lake. And then we drove through the sandstones, saw how they were getting into the lake, and eventually got to the lake sediments, and we were driving up these lake sediments for an extended period of time. All right, so what's my research focus? I look at the chemistry data and integrate it with these geological stories. So I work with the team, I work on these sedimentary stratigraphy. How can we tell the story? How do we understand what happened here? And then I look at the geochemical data and say, how does this fit in, and how much can we learn? I don't want to just learn about what happened right here. I want to learn about anything I can about Mars. And so when I look at a sedimentary rock and I try to understand its story, I think about each of the different influences. And I call this source to sink. There are different names for it, sedimentary rock cycle. But what we know about that rock is that the particles in it came from some other kind of, usually on Mars, volcanic rocks, occasionally some other sedimentary rock. So usually we have volcanic layers somewhere outside the crater. They get broken into particles by wind or impact or some form of erosion, water, and then they get pulled into the crater. They can be pulled in by wind or water, but they could be sorted by that process. So what we're seeing in the crater may only be a fraction of what the source rock looked like. We have to keep that in mind. So there's some sorting process. Those pebbles get into the crater. They may sit in the lake. They may be affected by stuff from the lake that's precipitated while there's actually water interacting with the surface and the ground. Or they may just be deposited in a dry environment. In either case, they eventually get buried. And once they're buried, that's when groundwater seeps through and cements the rock, either by altering these grains or by adding salts. So then, many years later, it's exposed and could be affected by the exposure. But for the most part, when we're looking at these cemented rocks, we just need to be able to tease apart these different factors. And so one of the first projects was looking at, there was river rocks coming across. And I said, the chemistry of these rocks depends on their grain size. So when we look at the coarser grained rocks versus the finer grained rocks, and these are kind of binned grain sizes, this is a plot against aluminum. The coarser grained rocks have a lot more aluminum than the finest grained rocks. And this is true not just for aluminum, but it's also true for silicon and sodium. Finer grained rocks, on the other hand, have a lot more iron and magnesium and titanium. And so, interestingly, aluminum, silicon, and sodium make up one of these igneous minerals called plagioclase, which forms whitish crystals. Now, we looked in all of these different river rocks, and we finally found one where there was actually a pebble about the size of your fist that had been carried in a river. So that river was even deeper than knee to waist deep, right, to carry a rock the size of your fist. That one rock the size of your fist really helps interpret this. So we did a lot of other statistical techniques I wasn't going to talk about today, but here's that rock the size of your fist. Its name is Harrison. We name everything. And Harrison is a volcanic rock. And it's a volcanic rock that contains these long laths, these huge plagioclase crystals that are actually up to a couple of centimeters long of a light-toned mineral called plagioclase. And it's set in a dark mafic basalt, so a kind of classic dark basaltic volcanic rock. This type of rock in particular, if you break down a rock that's like this, you're going to break it down and have these light-toned large crystals and a bunch of fine-grained dark crystals, just because when you break it down physically, the easiest thing to do is to break the crystals apart from each other. And so if you break a rock like this and then you carry it in a river, your coarsest grained rocks are going to look like these light-toned minerals, and your finer grained rocks are going to look like the dark-toned ones. And that's pretty simple, but it's exactly what we see. So for the whole river system, we saw that trend, and it seems like, this may not be exactly what every rock up there looks like, but this type of volcano, this type of rock would produce most of the chemistries we see. And we've been digging into that for a little while. There's a couple of things we can do with that. One, okay, we can say sorting was a major effect. But two, we can say, okay, this is the kind of volcanic rock we formed. What was the volcano like? And so we could get the mineral chemistry, we get into the details. We get into the mineral chemistry of these plagioclase minerals. This is work from one of my postdocs, Valerie Piré. It's the paper that came out earlier this year, where we actually were able to model exactly what the magma went through to produce a rock like this. We don't know for sure. We said, what's the most simple case? What is the most simple type of volcano that could produce this rock, or that could produce all of the minerals that we saw? And it turns out you need two different magma kind of evolution pathways to produce all the minerals we saw, but we can constrain them to a decent extent, right? We can say that one of them had almost no water, and one of them had about 0.5 weight% water, and we can kind of get into the details of the oxygen fugacity and stuff. So that's been one fun direction we've gone in. And the other one was that we said, wow, we've seen all these volcanic minerals in the middle of this crater, in these sedimentary rocks, but they actually look like volcanic rocks very frequently. And so how cold was it that they weren't weathered or changed much at all? So I've been working with a different postdoc on that, and he's gathered data from around the world, but especially had worked on some samples he had from Iceland and Idaho, looking at rocks that are similar to that are carried in rivers. And what happens as they go downstream? Well, there's chemical weathering. And so this is a kind of a ratio that we use for chemical weathering, the CIA. And if you're higher up on the ratio, it's a warmer environment. If you're lower down, it's colder. Now, interestingly, the rocks in Gale Crater are 3.5 billion year old mudstones, but they are less weathered than many of the rocks we see in rivers in Iceland today. So these are fresh volcanic rocks in an icy place that are being carried downstream. So we are really excited that these were habitable environments, but we do need to face that they were probably still really cold. It's always been hard to justify how Mars had this much water and had this much water for this much time when Mars is further from the sun, and 4 billion years ago, the sun was only 75% as bright as it is today. So in order to have liquid water on the surface of Mars 4 billion years ago, it needed to have twice the greenhouse effect that we have on Earth today. And so it looks like, based on these measurements, that we need to be careful in seeing these lakes and these rivers as something that would exist in Iceland or Antarctica today, as opposed to something really super clement or anything like Houston, right? And so when we're thinking of these Mars rivers, this has been one of the first ways we've been able to kind of pin down what the climate would actually be like, and it's similar to Iceland. Okay, I think I accidentally reviewed that slide. Okay, so that's some of the work my group is doing. Now I just want to talk about where we are right now with Curiosity. We're in that purple trough, which is where we identified the strongest signatures of clay before landing. It turned out it was a little bit disappointing when we got this first picture of what the trough actually looked like. It's a beautiful picture, but we like rocks, and most of this is kind of sandy, dusty, pebbly, and there are very few rocks actually in most of the trough. There are rocks on these ridge lines as you go across, but the middle is actually kind of pebbly, which was surprising for us, but they're mudstones and they are clay rich. So that's been exciting. And so we're working on the papers now for this unit. They'll hopefully come out in the middle of next year about, but we found a variety of clay minerals that are telling us even more about the climate in the ancient environment. And where we are right now, this was right before we crossed the trough, and now we're on the other side of the trough. So here's a picture that was taken 2 days ago. We're on the other side of the trough. We're looking up the hill. The next major phase is this transition between the clay-rich unit to the salt-rich unit. And that's a big deal. We've been hoping to go to that transition since before landing, because that's what we're hoping will tell us part of that story, help us capture what kind of environments show this transition from clay to salt. Did the whole lake dry up? Did it just start to dry more often? Has that area just been crisscrossed by fractures and late fluids that had salt in them more? What does that transition look like? And it's kind of cool that it's sort of marked by this light-toned sort of bathtub ring, and you can see a few plateaus. But it turns out, and this is looking kind of close to uphill and just a little bit to the right of uphill. It's kind of southwest, but it's close to uphill and just a little to the right. This is the direction we'd love to go. But as you can see, the driving in this particular direction would be a little treacherous. So we're going to go skirt around it a little further rather than kind of cut down into these craters with deeper sand where we might get stuck. And so this was one of the pictures taken yesterday of how we'll probably instead skirt around this much flatter, friendlier driving zone to get up and then turn to the right and get into those higher layers and see what happens as it gets drier. And so this mission has a lot of exciting stuff going on, but also we're really looking forward to February because on February 18th next year, the Perseverance rover will be landing in Jezero Crater. And Perseverance looks very similar to Curiosity. It's got the same kind of body. We did update the wheels, those are new. And this one, instead of being a roving laboratory, is a roving sample collector. So it has a few instruments. It'll have that same laser instrument and a few other instruments like the one on the end of the arm to really look up close. It can brush off the rock and look up close at the chemistry. This one can actually map out the chemistry in that postage, in that penny size. In this case, it's kind of postage stamp size, pretty similar box. And it can also look at some of the mineralogy, but we used a more remote instrument this time. It doesn't have the same laboratory capabilities as Curiosity, but it has some. It'll scope out things. And then what it does have is a big sample collector and about 43 sample tubes. And so its job is to drive around and pick samples based on its survey instruments and collect them into sample tubes. It'll hold on to those tubes for a little while, and later it will drop them on the ground and another mission will come. And eventually these will be the first samples we've ever returned to Earth from Mars. And I'll show you the mission architecture briefly on the next slide, but its goal is to collect samples. And we wanted to pick a landing site that would represent, the stories we want to understand from early Mars, and maybe one of the most likely sites to be a home for ancient Mars life, right? Where would Mars life have lived? Now, this might be getting familiar to you at this point, but we really like those deltas, right? We really like those areas, right, where the river comes in, hits a lake, and deposits all its sediment. So this is part of Jezero Crater. It's about 27 miles across. It's smaller. This is the rim of the crater. And I've just shown right here, you can see an ancient river that came in. It's actually really clear here. And here are the delta deposits on the floor. So we'll hope to go drive around to these delta deposits, drive around, collect some samples potentially on the rim of the crater. And then this mission may actually drive right out of Jezero Crater and drive up into kind of the hinterlands and see what's actually up there. This spot is a special one for a couple of reasons. It's the hinterlands, the area where all the sediment is being sourced from, is one of the oldest areas on Mars. And it shows that original record of water interacting with volcanic rocks 4 billion years ago. That's the stuff that's coming downstream and getting placed into this delta, which is, again, a lake sitting there and accepting sediment from this river. This sediment also contains some of the mineralogical signatures of carbonate, which I mentioned is very rare on Mars. Normally we see sulfate, but carbonate or limestone, well, limestone is calcium carbonate. In this case, it's magnesium carbonate. But that type of rock is excellent at preserving fossils on Earth. It precipitates quickly. It precipitates in places like the Bahamas in shallow, warm water. And so we're pretty excited to finally find some of that on Mars and collect it and bring it back and test it. We've seen it once with the Spirit rover, but this is a much more clearly identifiable deposit around the edge of what is a known ancient lake. So again, Perseverance will go up Perseverance is on its way. It'll land in February. It'll leave that box on the ground. And then this dark blue mission will come from Earth, land. It has a lander with a little launcher and a small rover that can go collect the samples from the ground, bring it back, put them in the launcher, and launch them into orbit around Mars. And you need a third mission that comes from Earth, picks them up in Mars orbit, and brings them back to Earth. And that'll be in the early 2030s. But we are really excited. Like said, I will get to be a participating scientist on that mission. So to help pick out the samples is really thrilling for me right now. So that wraps up what I wanted to share with you. Thanks for listening. Thanks for inviting me out. And I'm really happy to take any questions.
Thank you so much, Kirsten. That's a great summary of what you're doing there with the chemical and the water dimension things. Can you comment a little bit on what the biologists are saying about what you found in terms of the temperature of the water, its chemical content? What do they make of this that you're finding so far? And what do you expect in the future in that domain? What's the most surprising thing you found, Frank, you didn't expect here? Thank you.
Yeah, so let's see. On this mission, we did find, actually, one of the things that was surprising is we found some organic material, and we don't know, organic in this case, just reduced carbon bound to hydrogen. It was also bound to a lot of sulfur. We think it's some kind of a kerogen, which is the type of organic material that's present in meteorites. The cool thing about that is not necessarily just that it exists, and really we don't know the origin. It could be biological or something like that. Could be abiological, which is where we're going to lean until we have something to show otherwise. The cool thing is that it was preserved. The cool thing is that we had these reduced, long-lasting lake environments that have been well preserved enough to keep carbon in an organic state from 3.5 billion years ago. Even if it wasn't life, it still at least tells you there was kind of food, right, for life in the lake. And I talked about how hard it is. If you look at the rocks in Australia or in the Canadian Shield, right, these ancient rocks from 4 billion years ago on Earth, it is really hard to find the organic carbon in them. And so the fact that we just drilled about 10 times into this ancient lake on Mars with Curiosity and immediately found organic carbon is actually really telling us that those ancient environments are well preserved on, you know, our neighboring planet, right? And I was very surprised that we were able to find that much much variety of organic carbon preserved for that long. I've also been surprised by how long the lake lasted. There have been a whole lot of different discoveries. One other unsurprising one is the observation of methane in the Mars atmosphere. Methane on Earth is 95% biologically produced, but it can be produced abiotically. The weird thing about finding it on Mars, we had some suspicions about it because of some earlier observations, and so we made sure we could detect it with this rover. What we found is that most of the time there's no methane. Every now and then there's up to 7 parts per billion methane, but then the next time we check, it's gone again. We think, based on all our physics calculations, that methane should last in the Mars atmosphere for 300 or so years. And so there's 2 mysteries, and one of them is where the methane is coming from, and one of them is where is the methane going? And we've got actually a whole variety. There's orbiting instruments now looking for it, and I think one has found it and one has never seen it. So there's a huge debate about the atmosphere of Mars today. So that's one of the modern Mars mysteries, as well as the ancient Mars mysteries.
Yeah, this is Bernie Rosenbaum. A question on about probably 10, 12 years ago, I was reading an article where the author included some pictures of the sidewalls of a deep craters or steep walls. Anyways, over the seasons, he was speculating the changes you see were due to water seeping down the cliff face and causing some erosion. Is that still the interpretation of that data?
It has been debated a lot. Let me see, I think I have an extra slide with those. Yeah, so we call them recurring slope lineae. And there are some, steep walls of craters around the equator, and it happens during the summer. Over the course of the summer, you see these dark streaks slowly extend down the crater. And if you can see the timeline, it actually takes months for the dark streaks to extend down. And then over the winter, they seem to disappear. And it's been a lot of debate about whether some of the salts we've seen on the Mars surface, like perchlorates, are very hydrophilic and can actually reduce the freezing point of water. So if you have enough perchlorate, you could have a little tiny bit of a liquid brine. So that was the debate for a long time. The current thinking is that these are dry slides. For the most of the current thinking is that they're dry slides. So they've shown that they actually occur on slopes that are consistent with dry particle movement. And like I showed with the dark sand in Gale, there's this really strong albedo lightness contrast, where if you have dust, it looks light. And anytime the dust gets moved or obscured, you get these dark patterns. And in Gale Crater, those are the dark sand dunes. But it can be really dependent on the amount of dust. And so they think these are slides.
So it's wind or air activated as opposed to water then. It's causing the motion.
There's definitely some disagreement on that point, but I am inclined to think so.
All right, excellent briefing. I really enjoyed this.
Well, Kirsten, I have a question. So Curiosity has obviously outlasted its planned lifetime. What was its lifetime and what is it now? And now what is Perseverance planned lifetime and what do you really expect to get out of it?
Yeah, so it really depends. Well, there's always this risk on Mars of literally anything going wrong, right? Of a gamma ray hitting your computer and just knocking out your communications or something along those lines. And Curiosity and Spirit and Opportunity all experienced some version of that exactly. With Curiosity, we used a radioisotope nuclear power source, right? And that's what's housed in this kind of little back compartment. And we use the same thing for Perseverance. So that is providing heat and energy to the rover, but it's nuclear decay. And so it decays, and I don't remember the exact half-life, but we anticipate that it would, when we first landed, people were saying 10 years, and now they've really extended that a bit. So we're thinking more like 12 or 13, and that's partially because we've gotten more efficient software so that we can drive a little more efficiently. But at some point, you still run out of that power source. And so if the power is the first thing to go, then we have another 4 or 5 years, and somewhere in there towards the end, you lose the ability to drive, but you can be a stationary research station for a little bit, and then eventually it gets too cold. And Perseverance has the same body and the same source, so on the order of 12 years, if that's the thing to go, right?
Okay, thank you.
Kirsten, in the persistence of the ice on the surface, is that consistent with the atmospheric pressure and the sublimation rate of water ice, or is it being resupplied constantly? It looks like over several billion years, it would disappear.
Yeah. So with Mars, the obliquity can change really dramatically. So Mars currently has an obliquity very similar to Earth. We're at 23.5 and it's at like 24. It's very similar to Earth. And so, but the obliquity changes more dramatically than Earth over time, or the tilt of Mars. And that might cause a lot of kind of over time major ice movement from what's currently the poles to different parts of Mars latitudinally. And so right now, the poles are we think they're slowly accumulating, that actually ice from lower latitudes is still being vaporized and moved to the poles, which is the coldest trap that it has on Mars today. So the poles themselves are stable right now, but there are areas in the mid latitudes that are not as stable. We actually, in 2008, we landed the Phoenix lander up close to the pole, I think 82 degrees or something, and dug down, and it took about 5 centimeters, a couple inches, we hit pure ice. But in hitting that pure ice and taking off that 5 centimeters of dirt, the ice started to sublimate immediately. And even with orbital imagery, we'll sometimes catch a new crater that's hit up towards the north. It'll expose a bunch of ice, and that ice will start sublimating, and it'll accumulate on the poles. So right now, the poles are the sink for all of the ice. but there is ice that's not necessarily in equilibrium that's slowly migrating there at this point.
Okay, so the atmospheric pressure is not such that you're continuously losing water molecules to space?
You do lose some. Yeah, you definitely, so you continuously lose some to space. Interestingly, I had one picture from I said there was a global dust storm in 2018, and we had this resource on the ground and an orbiter that was mapping that. So it was very helpful in learning that there's approximately decadal giant dust storms that cover all of Mars in dust, lift all this dust into the upper atmosphere. That's actually what drives a lot of the water loss to space. So it's these big, approximately decadal events that lift the dust way up high. Along with that, they bring a bunch of water up into upper atmosphere, and then it just gets knocked out into space. There's no magnetic field. There's nothing protecting it from the solar wind. So on Earth, we get the aurora instead. It's just pretty, and the ions get deflected away. On Mars, those are just blasting away the upper atmosphere. But it's mostly hydrogen, and the escape rate is usually pretty low. It's higher during those events, but the ice caps actually have a really substantial amount of water compared to that. They do shift seasonally. The ice shifts from the North Pole to the South Pole, as well as the addition from mid-latitudes. And with that, the atmospheric pressure can actually swing quite a bit between on the order of 4 millibars to 10 millibars. Just because of whether all the ice is stuck at the pole or whether it's in a gaseous state while it's transferring to the other pole. So it's kind of, it's an interesting sort of dynamic system. Oh, and the one other thing I want to say is the poles have actually trapped enough ice that if you took the two poles and melted them completely, you could, and if Mars was a spherical ball, this is an odd unit, but if Mars was a spherical ball, you took both poles and melted them completely, you would cover the entire planet in 22 meters of water. So there's actually, while there is a constant escape, there is substantial water locked up in those poles.
And how much water over the surface?
22 meters.
That's
Wow.
That's an amazing figure. Yeah, I go out and talk to kids about, I tried to go to Mars with my friend Mark Craig, who I see is listening in today about 30 years ago. And we got close, but we didn't make it, but my grandchildren are going to be there. And I want to tell them today what to look for.
Yeah, we've got to get them into a place in between. It's so cold at the poles. We've got to get them into a place in between, right? The equator's warmer. You got to get the ice though. The ice is all at the poles. So we got to actually use that mid-latitude sort of unstable, over long periods of time ice that's buried. And we've got to map that out better so we know where the resources of water are that are a little bit warmer than the poles, because the poles get to like 220 Kelvin. It's very cold. No, sorry, minus 220 Fahrenheit. I got my units all mixed up. Minus 220 Fahrenheit. It's very cold at the poles. There's lots of water, but it's really cold. You want to find a place for the people in between.
Stokes, when will this video be available for the recording?
Well, hopefully within a week or two.
And what would be the source with which to achieve that? See it?
It'll be on our NASA Alumni League website.
Great, thank you. A lot of Earth geologists would be really interested in seeing this.
I agree. It's been a super presentation for geology.
Absolutely superb.
Thank you.
Well, any other questions or comments for Kirsten? Well, Dr. Siebach, I mean, this has been an outstanding presentation. I thank you so much for your time and presenting to us old NASA retirees. I think we've really enjoyed it. It's been one of the better ones. So let me leave you a round of applause for Kirsten.
Thank you. Thanks. It's fun. Thanks for the questions.
Okay, I'm going to stop recording now.